Anyway, I'm Jeffball. I'm talking about analyzing SUID binaries. Specifically, we're going to look at one case study I found on VMware Fusion. We're not going to look at the 30 other ones or 10 other ones I looked at that didn't have bugs because they're obviously not as interesting. But instead, we'll look at the one that did have bugs and still does have bugs, VMware Fusion. I also have VirtualBox installed, which had some SUID binaries, but when I looked at them, they weren't, the bugs weren't as shallow, and so I tended to look at the more low-hanging fruit. So let's just get started. The obligatory intro slide. I go by Jeffball. That's my Twitter handle. So if you want to, you can ask me questions there, or again in the Discord. I'm a senior researcher here at GRIMM. I've been here for about 3 years. I do a lot of binary analysis as well as web stuff and general reversing, or mostly whatever needs to be done. And then I'm also a part of the DEF CON 949 group as well. And so I've done a lot of things with all of the people there and had a lot of fun doing that. So next, we're obviously getting to the next obligatory slide, which is the motivation slide. Well, why do we want to target SUID binaries? Why not look at the kernel extensions or privileged services? And the answer is SUID binaries are just very hard to write correctly. When you're looking at normal software, say a text editor, it's not a problem if you rely on environment variables being sane. And so if your environment variable says the config files are loaded in this location, you can trust that, because if someone were trying to attack that program, they would also be the ones who started it and changed those environment variables. And so it's not really crossing a security boundary for a user to set weird environment variables and start the program, because they're the ones who started it. And if they wanted to, they could just start another program. So it doesn't really gain you anything as an attacker to attack a normal program like that. But with SUID binaries, they run as root. Essentially, the operating system sets a special flag that says, run this program as the user who owns it. And we specifically look at ones that are owned by root. And so when I run this program, the program becomes the root user until it's done executing. And so I actually do gain something from messing with the environment variables or other files that the program may use, because I'll start it, it'll become root, and then if I can gain control of that program, I then gain control of root. And it's just a local privilege escalation. The typical example for SUID binaries is the ping utility. Most OSs don't allow you to write to raw sockets, which is one thing that's needed to send ICMP packets and receive the responses. So the ping utility is often marked SUID so that it runs as root. That way it can write to raw sockets, send the ICMP request, read back the response, and print it out. So when I, as an unprivileged user, run it, it becomes root, sends that stuff out, gets the replies, prints it out, and then exits. And unless I have some way to exploit ping, I can't become root. And so that's what we're going to look at. It's an easy way to get root as compared to looking at something like kernel vulnerabilities, where you have to ensure that the kernel doesn't crash. And so you'd have to do some type of heap overflow and heap spray in order to exploit it. And then if you don't clean everything up perfectly, the operating system will crash and you'll lose anything that you just gained. You can't really exploit an operating system that's crashed because it's now dead. And so you need to make sure to clean it up, which is rather complicated. Whereas with SUID binaries, they can crash. It's not a big deal. We'll just restart them. And so the reason to target SUID binaries is just a combination of the easier exploitation and the more exotic attack vectors, such as the environment variables or files. Additionally, you need to make sure that there aren't things like race conditions. So if you read a file once, and then later on you close and reopen that file and read it again, the content may have changed. And so you can't really even trust the file system to be correct. And so it's a much harder thing to program. And so because they're hard to write securely, they tend to have more bugs that might allow a privilege escalation. And so it's just kind of a combination of the two, those 2 points as to why you might want to target them. Next, you'll obviously want to go about finding any SUID applications. This little find command will find any of them on your operating system in the /applications folder. I chose to look at the /applications folders because on Mac OS, that's where you would find third-party applications. Specifically, I didn't really want to look at the Apple ones as much because there's more people that look at those since they're included in the default install, and generally the OS vendors like Apple do a better job than third parties at writing code, and specifically SUID binaries because they're so hard to write. Any third party might not have the expertise to write one securely. And so I just ran that find command and located all the SUID binaries and then started the analysis. The first thing I did was use DTrust. DTrust is a tool on Mac OS that just prints out all the syscalls. And so if you're familiar with strace on Linux, it's an equivalent program. The syscalls will then tell us what the binary is roughly doing. It'll tell us the files it opened, any files it tries to execute, and anything of that nature. So we'll just run those out. Let me just switch windows real quick. Oops. All right, so the first thing I did here, which you can see, is I ran that find command with a little modification to actually copy them all to this directory. This is all of the ones that VMware installs. As I was saying before, it installs a number of them. Like we're going to look at the Open VMware Fusion services and Open VMware USB, but it also installs some debug ones, some statistics ones, and some ones that run the actual VM. And those ones are much larger, and they might have more complicated bugs that I stopped before finding. And so as I was saying before the meeting started, I might look into those more for bugs. But what we're actually going to do is we're going to run them in DTrust and then record the output to temp trace the name of the program. That actually takes a second, so I've already done it. But then we're just going to want to see which ones execute a binary. And so this is the output of DTrust. And as you can see, Open VMware Fusion Services is trying to run the program /content library services VMware Fusion Services, given the name Open VMware Fusion Services, and you would expect that it's trying to start a binary named VMware Fusion Services. So it's not really a big surprise. And same with the VMware USB Arbiter services and opener and VMware USB Arbiter services. Both of them are failing, as you can see, to run that program. And the obvious reason is the /contents directory does not exist. That isn't a folder. It's clearly doing something wrong. And so we're going to want to just kind of investigate that a little bit more. Ooh, sorry, my computer froze up there a second. So what we're going to do is we're going to open it up in IDA, specifically with the decompiler, as it generates some nice C that I've cleaned up a little bit there. So this is what we have for main. The first thing it's going to do is going to cause this sanitize environment function. This function just iterates over every environment variable and removes any that start with -env, env, or shell ops. And specifically what it's doing there is trying to avoid vulnerabilities that may occur if they don't clean out the environment variables. So this is one thing that you have to be sure to do when you're writing a SUID binary, that if you didn't, it might cause problems. The other one that you might notice there, right here, is it's cleaning out any environment variable that has a value that starts with an open paren, close paren, and brace. If you're familiar with that sequence, it's actually defining a function in bash, which is part of the shell shock vulnerability. And so I assume this was a mitigation they added in response to shell shock to remove environment variables that have that sequence in them. So this is just one instance you'd have to be thing that you'd have to do to clear out the environment variables for SUID binaries. Next, it's going to go into a privilege lowering process. What it's going to do there is it's going to get the effective UID, which is 0. It's going to save it to a global. Then it gets to the actual UID, which is my unprivileged user's user ID, and it's going to set it to the effective one. Essentially what that's doing is, even though this binary was started as root, it's going to lower it down to the unprivileged user that started its privileges. And so until they call the opposite sequence, it will be effectively running as my unprivileged user. So the opposite is just to set the effective UID back to the original one, which is 0 or root. And it'll do this just before it does anything it needs that is privileged. This is another mitigation that you need to use when writing SUID binaries, is because if you do everything as root, if you take one false step or do one thing incorrectly, that could easily lead to a vulnerability. So they are trying here to just avoid, with these two function calls, avoid some of the common pitfalls in SUID binaries. The next function they're doing is just local location init. It's looking up this string in a list of tools. I'm going to switch back to the slides one sec. It's looking up that string in this list of tools and getting the number there. We'll see a little bit more next, what it's doing now with that number, but it's saving it to this number of up counts, which I'll show you what it's for in a sec. And then the other thing that it's doing is it looks up the string USB arb daemon file in this location get root function here, and it returns this string /content library services VMware USB arbitrary services, which is the program that we saw it tried to open. Next, we're going to look further into the location get root function to see why it tried to run this without prepending the /applications VMware Fusion that you would expect. So this is the location get root function. It's essentially just trying to find the daemon's path. Up at the top, we see this host info get module path call, which is just a fancy wrapper around the NSGetExecutable path function, which on macOS is just how you resolve the currently executing program. And so it's just getting the path to the program we're opening or the SUID opener binary. Then it calls real path, the first unlined one. And all that does is it resolves any symlinks to the main executable. So if we were to symlink to the SUID opener and then run it, this would resolve the real path to that. And then it falls down into this while loop at the bottom and calls this string reverse care search. It's essentially finding the last string in the path, or splitting it up into the directory name and the executable into two parts. And it zeroes out the slash. So it's getting the directory that it's in. It does this for the number of up counts that we saw before when it looked it up in that tool list. It does that 4 times, and so we're essentially removing 4 slashes. And so it's going to go from the SUID directory path, the SUID binaries path, chop off the executable name, and then go up 3 directories until you have what would be the path /applications /VMware Fusion. And then it's going to, at this last underline function, it's essentially a custom version of scanf, where it's just going to combine that path name that is just generated with the path that we looked up before, the /contents, library services, so on. And so that's how it resolved the path to the daemon that it wants to run. We'll take a look at how we can exploit that on the next slide. This is just a further deep dive into the NSGet executable path and the real path functions. This is just a little toy example to show it off, but essentially we're going to call the NSGet executable path function to get the path of this executable. We're going to path it to the real path, and then we'll just print them both out. Nothing too complex there. If you look on the right, then the first example, we run it directly from the real path program. And so the NSGet executable path returns this path right here. And then after we path it to real path, it gets rid of the /. Next, we run it as a symlink, and we can see that the get executable path function gives us the path of the symlink, but when it's passed through real path, it gives us the target of the symlink. And in the final case, we can kind of see where we're leading with this and how VMware Fusion was vulnerable. Is if we make a hard link and then run it from the hard link, we can see that it's actually resolving to /hardlink here, but instead of going to real path, it gives us hardlink. So we've got /users Jeff GRIMM hardlink. And so that essentially lets us control the path of that VMware Fusion uses. So if we go back to our previous slide, you can see the host info get module path actually becomes untrusted user input, because the user can control through the hard link where the SUID binary is, and thus we control this variable. Then when they .. /up, there's just removing directories that we control, and we still end up within our user controllable directory. And so we can kind of take a look at how you might exploit this. It's very simple. You don't have to do anything too complex, and you don't have to clean up afterwards like you would a more complex kernel or system process exploit. And so the first thing we'll do is we make the directories content library services, and then we'll also make one that's ABC. The reason we make an ABC directory is we're going to put a hard link to the SUID opener there, and then it will .. out of C, out of B, and then out of A, and then go back down the contents library services and find the VMware USB arbitrary service. And so essentially, we're just exploiting this directory traversal by adding a bunch of directories so it can go back up and then back down and find what we want. And so we'll compile our payload and put it at the expected location. We'll make the hard link from the SUID opener to our ABC directory with an executable in that, and then we'll run our executable. It will resolve the wrong path and then launch our executable. And so it's a nice simple exploit. We can take a look at what that looks like right here. We'll just run it. It will start the SUID binary, which then starts our payload, and then we can just, our payload is a simple netcat listener. We netcat to it, and you can see we got root. And so just like that, a nice simple exploit, we now have root. So after we reported this to VMware in version 11.5.2, they actually released a patch. Unfortunately, that patch only fixed one of the two binaries. As I mentioned before, there's the VMware Fusion Services SUID binary and the VMware USB Services SUID binary. It only fixed the Fusion Services one. Then in version 11.5.3, which is the current version, they released the patch that we're going to look at now. If you recall from the previous version of main, which it's essentially the same. The only difference is the underlying function call. Now it calls this privilege helper function, which checks the path prior to executing the service implementation function, which starts the actual binary. And so everything else here is the same. It's still going to resolve the same path, still is the same directory traversal issue, but it's first going to check the binary to make sure it's good. And if it's not, it's going to print out this warning message, invalid script code signing for, and then print the path of our directory. We're going to take a quick look at that privilege helper. The rest of it isn't really too worthwhile to look into, but we can see it's going to create a string with this little identifier and anchor Apple generic and anchor trusted cert leaf VMware Inc., which is essentially just a code signing policy. And then it's going to call this sec static code check validity. There's not much you really need to know about this other than it's checking the code signature on the binary that we give it to see that it's signed by Apple and that the common name of it is VMware Inc., and that it matches the expected identifier. As we can't get a certificate from Apple that says we are VMware, we shouldn't be able to sign our payload with the correct cert, and thus it'll fail. However, there's a new issue with this SUID binary. Again, it kind of illustrating how hard it is to actually write SUID binaries correctly. We check the binary here, and then we run, we start it afterwards. as I mentioned before, race conditions are a big problem in SUID binaries, and this is just a kind of a classic example of a race condition. They check the code signature at the underlined line, but then they actually use it in the next function call. And because of those two different uses, we can actually put the correct executable when the code signature is checked, and then swap it before it's actually started. And so we can kind of win that race condition there. And so let's just take a look at a modified exploit that will actually do this. Again, we create the same directory structure. This time we write our payload to the payload file, and we hard link to the SUID opener, and then we start this swap.sh shell script in the background, which is the shell script down below. All that is going to do is it's going to continually switch between creating a hard link to the legitimate binary and a hard link to our payload in the expected path. And what this will do is we're hoping to write the legitimate binary when it's doing the code check, and then after the code check is finished, but before the executable has started the service, we write our payload. And so if we can win that race condition, we can run our payload as root because the SUID binary is kind of tricked into running it, despite the code signature check. And then finally in the exploit after the swap.sh is started, we just continually start the SUID binary, hoping to win that race condition. And now we can just jump to that. Hold on one sec, I've got to switch snapshots. That was version VMware Fusion 11.0, and this new one is 11.5.3. Oh, all right. So this is 11.5.3, which is the latest version of VMware Fusion. Unfortunately, this bug has not been patched yet. So it will work on most versions of VMware Fusion. All right, so you just start up the executable, or start up the exploit. Sorry, my VM's being a little slow. It's going to run, and you can see it's failing there to win the race condition, and it just keeps trying. Once we win, I can use the netcat listener again. Ordinarily, this is a little bit faster, but again, my VM is rather slow while presenting, having another VM open. So eventually it will win. Ordinarily, this takes only a few seconds to win as it goes rapid fire. Oh, it looks like it won. And so now we can netcat to our payload, which is running, and again, we get root. So not too complex there. It is a little bit more complex than the previous one due to the race condition, but it's still much easier than any type of kernel exploitation that you would have to do. So that exploit is just a small shell script, although another user has submitted a pull request to Metasploit with this exploit. I believe it was the GitHub user Hoodie has submitted one. So it actually has made its way into Metasploit. So hopefully VMware fixes it soon so that there isn't an open exploit for VMware Fusion with the Metasploit module. With that, that's kind of the end of my presentation. The code and write-up for the first exploit is in our Not Quite O-Day Friday module. If there's any questions, feel free to ask them and I'll answer them as best as I can.
All right, thank you, Jeff. So if you have any questions, type them here in GoToMeeting. Definitely check out the GitHub for a lot more. I know it's hard to follow technical talks like that, so being able to get your hands on the code makes it a lot easier to understand the principles.
Yeah, sorry if that was a little bit too much in the weeds. A lot of my talks end up that way because it's just I like to kind of see those type of details. So.
No, absolutely, very helpful. All right. Can you please share more link to slides?
Sure, I haven't uploaded these anywhere yet, but I will when I do. Um,
All right, well, if anybody has any more questions, you are welcome to chat with Jeff over in Discord expert channel. It was awesome, thanks. So already some good feedback coming in. So that's your chance to talk in a little bit more detail, get under the hood, and definitely check out the GitHub link for more details. Jeff, good to see you
yeah,
again, appreciate it.
all right.
All right. Don't apologize, it was awesome. Working technical detail that takes a bit to soak in is great. That was such a great presentation. I forgot my question.
Well, the talks are recorded. So,
Yes, the talks are recorded and they will be posted once we get them and process them later.
okay, so hopefully that will be good. All right, cool. I look forward to watching all the ones I missed. All right, well, if anybody has any questions, I'll be in the expert channel on Discord. Later.